All right, this is the last section of chapter 1, section 1.6, significant figures. Let's share the PowerPoint. And whenever you take a measurement, um, you're going to introduce uncertainty. You use a large meter stick with only 1 millimeter resolution. You can only measure to so many digits. If you use some type of caliper or a micrometer, you can introduce more significant digits into your measurement, but you have to use the right tool for the given application. So the measured values are known only to within the limits of experimental uncertainty. Values of this uncertainty can depend upon various factors: the quality of the apparatus that you're using, the skill of the experimenter, and the number of measurements performed. In other words, if you can you repeat your measurements, you can average them and have a little more confidence about your results. The number of significant figures in measurements can be used to express something about the uncertainty. The number of significant figures related to the number of numerical digits used to express the measurement tell you something about that uncertainty. As an example, measure the radius of a Blu-ray disc using a meter stick. Assume the accuracy to which we can measure is plus or minus 0.1 centimeter. If the radius measured is 6.0 centimeters, we can claim only that its radius lies between somewhere between 5.9 centimeters and 6.1 centimeters. We can say that the measured value of 6.0 centimeters has two significant figures. Note that significant figures include the first estimated digit. Whoops, advancing the slides with my iPad. Okay, so we can write the radius as 6.0 plus or minus 0.1 centimeters. Okay, now zeros may or may not be significant figures. Zeros are used to position the decimal point, such as in the number 0.03 or 0.0075. Those zeros are not significant. They're only used to place the decimal point. When zeros come after other digits, there's a possibility of misinterpretation. As an example, let's look at something that's 1,500 grams, 1,500 grams. How many significant figures does this have? Well, it could have, it's at least has 2, but it could have 4 if those zeros really represent an accurate measurement. To remove the ambiguity, we turn to scientific notation. If we use scientific notation, 1.500 times 10 to the 3 grams gives us 4 significant figures. If it were 1.50 times 10 to the 3 grams, that's 3 significant figures. And if we were to write it as 1.5 times 10 to the 3 grams, that's only 2 significant figures. And yes, that is an error. It should be 10 to the 3, not 10 to the 2 in the slide. I am unable to correct it. That's straight from the publisher, and I tried to change it, but I can't. I couldn't. Okay. So scientific notation removes the ambiguity. And it's the same for numbers that are less than 1. So if you look at 2.3 times 10 to the minus 4, that has 2 significant figures, 0.0023. Now, if it's 2.30 times 10 to the minus 4, that's 3 significant figures. The 0 after the 3 is a significant figure, as indicated by the scientific notation. Now, when multiplying several quantities, the number of significant figures in the final answer is the same as the number of significant figures in the quantity having the smallest number of significant figures. And the same rule applies to division. let's see. Okay, I think that's all to say about that one. Let's look at an example. Um, the area of a circle is A equals pi r squared. Um, so using that 6.0 centimeters, let's calculate it. Pi times 6.0 centimeters, square that, you get 1.1 times 10 to the 2 centimeters. Now we know that pi, 3.14159, that's you can take that out to many digits, but the fact that we only have 2 digits, the 6.0 centimeters, we can only express that as 2 digits. So the calculator may give you an answer of 113.0973355. All those digits after the decimal mean nothing, and the fact the 3 means nothing because we only have 2 significant digits. So don't report your result as 113 centimeters. The result is not justified because it has 3 significant figures, whereas the radius only has 2. So the result has only 2 significant figures. I just circled it, or you can see it in the blue box. It's only 1.1 times 10 to the 2 centimeters. I would accept 110 centimeters. You don't have to express it in scientific notation. Okay. When numbers are added or subtracted, the number of decimal places in the result should equal the smallest number of decimal places in any term in the sum or difference. The smallest number of decimal places. So if we have 23.2 and 5.174, you put that into a calculator, you'll get 28.374. However, there's only 3 significant figures in the 23.2. The results often have different number of significant figures than the starting quantity. So the 23.2 has 1 decimal place, so the sum can only have 1 decimal place, 28.4. Now let's look at some more examples. The 1.0001 plus 0.0003. There's 4 digits after the decimal place on each one of those. So the correct answer is 1.0004. Now let's look at the second example. You end up the 1.002 minus the 0.998. You end up with 1 significant digit. I mean, the one of them has 4, another one has 3, but your result is only 1 significant digit, and that's just the nature of the subtraction that you carried out. In this book, most of the numerical examples and end of chapter problems will yield answers having 3 significant figures. In carrying out estimation calculation, we shall typically work with a single significant figure. And now let's talk about rounding. There's a new one for me in here, but we'll go ahead and listen to what the author has to say. General rule for rounding: the last digit dropped is greater than 5, then you increase the last retained digit by 1. In other words, 1.346 becomes 1.35. If the last digit dropped is equal to 5, you increase the last retained rounded to the nearest. You increase the last number retained rounded to the nearest even number. 1.345 becomes 1.34. Now that's a new one to me, but that's what the textbook has, and the textbook claims that this rule helps avoid accumulation of errors in long arithmetic processes. So we'll go with it. I'm not used to it. I would have rounded that to 1.35, but we'll listen to what the authors say. Now, if the last digit drop is less than 5, you leave the last retained as is. The 1.343 becomes 1.34. In long calculations involving multiple steps, it's important to delay rounding until the final result. This avoids error accumulation. In the textbook, values are rounded off to 2 or 3 significant digits for display. Okay, let's do an example. A carpet is to be installed in a rectangular room whose length is measured to be 12.71 meters and whose width is measured to be 3.46 meters. Find the area of the room. Well, how many digits do you have? You have 4 significant digits, 4 significant figures in the 12.71, but you only have 3 in the 3.46. So what will be the final result? How many digits should you have in the final result? I don't hear you. It's 3. You should only have 3. Okay. How many of these numbers should you claim? Our rule of thumb for multiplication tells us that you can claim only the number of significant figures in your answer as are present in the measured quantity having the lowest number of significant figures. In this example, the lowest number of significant figures is 3 and 3.46 meters. So we should express our final answer as 44.0 square meters. And with that, that ends the chapter discussion. We'll continue on with chapter 2 for this first week module. We want to get ahead of the game and not fall behind so that we can get to thermodynamics by the end of the semester. Okay. That ends that. Stop here.